Hello GATE aspirants, welcome to GATE Chemical Solution channel. This is 2-mark fluid mechanics question in the year 2021 GATE question paper. Please read the question very carefully and identify what is given and what we have to find out. So we will see the concept now, then we will go for the problem solution. If you are well aware of the concept, you can skip the concept explanation part and you can directly go for the problem solution. So this problem is related to fluidization concept. So we will see the concept. So let us consider a tall vertical column. Partly it is filled with a granular particles. It may be a catalyst or any surface area increasing particles also. These solid particles will be supported by the porous plate or distributed plate. The area of this vertical column cross section will be given as S0. Okay, the height of the solids will be given by the height of the solids will be indicated L. Okay, pressure drop across the bed is calculated by this U-tube manometer. Okay, delta P. Yes, let us say we are admitting air at the bottom of the plate. The fluid is moving on the solid particles. What happens? The fluid is exerting some upward thrust on the solids, right? Upward thrust, that is nothing but the buoyancy force. What happens? This upward thrust always tries to move the solid particles from this plate, but in the same way the solid particles will exerting a weight of the solids or the gravity force on the plate, right? So because of that, the solid particles, if you overcome this one, this upward this weight of the bed, then only the particles start moving. Okay, so since we are applying at low velocities, this bed height will be dominated by is more than this airflow, right? So if we increase the airflow, what happens? The pressure drop across the bed will be increasing. So this relation will be given by the Ergon's equation. So we will see later that one, that is not related to for this particular problem concept. We will see whenever that problem concept will come, so we will discuss that one. Okay, so the relation, so as the pressure drop is directly proportional to the airflow. So what happens if you increase the velocity of the air, how this pressure drop and height of the bed height will be varying? This is given by this relation. This is the superficial velocity, gas velocity versus pressure drop versus superficial gas velocity graph. This is bed height versus superficial gas velocity. Okay, since we are applying at the low velocities, since this is directly proportional to the velocity, the pressure drop is increasing. Whereas in case of bed height, so we are applying at low velocities, no, the bed height is not changing. Okay, so upward thrust will be increased by increasing the velocity, right? So if you keep on gradually increasing the velocity of the air, the pressure drop also increases, but the bed height will be remains constant. So if we reach one particular point, what happens? That is the point A. What happens here? The particles start to move, not completely moving. So some disturbance will be there in the solid particles. Okay, just some jerk will come to these particles. So it will little movement will be there overall the bed. Okay, that is indicated by this part. Okay, the disturbance coming over the particles, some jerk will be there. So little bit variation is there in the movement, the position. So that is will be given by this variation. So if we reach at this point, the velocity, the pressure drop across the bed will be constant. From this point onwards, the pressure drop will be constant from this graph, right? Okay, so but if you reach at this particular point B, as the bed height it reaches the point B, by increasing the velocity of the fluid, the bed height will be keep on continuously increasing. Clear? So at this point, the weight of the bed will be counterbalanced by the pressure drop. Okay, clear? So beyond that, if you increase the velocity, the pressure drop will be remains constant throughout the bed and the bed height will be keep on increasing. Okay, So this is called the condition of fluidization. It means the term fluidization and fluidized bed are used to describe the condition of fully suspended particles, since the suspension behaves as a dense fluid. So this is the condition of fluidization. So here initially what happens, so let's say this is the bed, these are the solid particles present at the bottom of the bed. At the condition of fluidization, what happens, the particles will be suspended, the distance between the particles will be increasing. So they are simply behave as a fluid. Initially their presence of density of the solids will be more and they are lying on the bottom of the bed, bottom of the tube, right? But in the case of fluidization, what happens, the upward thrust will be increasing more than the bed height, so the particles will start moving, that they are present as a they are completely suspended in the fluid, they are not simply lying on the bottom. Okay, that is the condition of the fluidization. Okay, so this is the fluidization condition. In the fluidization condition itself, the pressure across the bed will be constant, the height of the bed will be keep on increasing. So if you reverse the condition, so we have reached at this point at this velocity, right? So if you decrease the velocity of the air, what happens, again the pressure will be maintained as the same constant and the bed height will be again decreasing back. Okay, if you again decrease the velocity, if you reach at this particular point, and we will reach at this particular point in the case of bed height, okay, that is B point, the pressure drop will be lesser than the previous case. So again if you reach this condition, again if you keep on decreasing the velocity of the fluid, the pressure drop curve will be like this. It means pressure drop in the fluidized bed condition will be less than the in the fixed bed condition. Okay, if you decrease the velocity, whereas in case of the bed height will be more than the, since previously they are dumped into the tube and they are tightly packed. Once it is fluidized, the tightness will be little bit decreased. So since they are slowly settling down in the tube, and that much tight packness will not be there, since they are little bit loosely packed in this case. That's why the bed height will be little bit more than the initial condition. Okay, that's why if you decrease the velocity up to this point, so the bed height will be not changing, it is constant from this point to this point if you keep on decreasing the velocity also. So since it is little bit higher than the fixed bed condition, whereas the pressure drop will be less than the initial fixed bed condition. Okay, clear? So once if we reach this condition in this case and this condition in this case, if once again if you start the fluidization, if you increase the velocity, the fluid the disturbance will be started at this point only, that B point. Initially the disturbance will be started at A point, right? In case once fluidized bed will be, again we are coming back to the once fluidized bed is returned back to the fixed bed condition, and again if we start the fluidization, what happens, only the fluidization will be starting at this particular B point only. So because of that, this is the minimum fluidization condition, this is indicated as the minimum fluidization condition. Okay, the velocity that required to start the fluidization is called as the minimum fluidization, or that condition is called as the minimum fluidization condition. Okay, or incipient fluidization condition or incipient fluidization velocity. Okay, at this condition what happens, the pressure drop will be counterbalanced by the weight of the bed weight and upward thrust of the fluid. Okay, since I have mentioned that the pressure is directly proportional to the velocity, right? Actually this is the another concept. When we come across any problems of related to this concept, we will discuss all those one, but simply I have represented here the relations for laminar conditions and turbulent conditions in the case of fluidization. Okay, so the particles are quite small, flow in the channels between the particles will be laminar, and the pressure drop across the bed will be proportional to the superficial velocity, that is V bar naught. This is given by the equation Cauchy-Kármán equation. So this is the pressure drop with relation to the superficial velocity, so directly proportional in case of laminar condition. In this case NRA of the particle will be up to 1. Okay. For higher Reynolds number, the NRA of the particles will be that is greater than 1000. In that case the pressure drop relation with respect to, this is the viscous portion of the fluid, this is the kinetic portion of the fluid. Okay, this relation is given. So this derivations under we will discuss whenever the problems related to this concept will comes. Okay, so if you want to know all this one, you can refer textbooks. For any range of fluids, the pressure drop is simply a sum of the viscous losses and the kinetic energy losses. So that is given by the two terms previously I have mentioned. Equation 1, sum of delta pressure drop per unit length is simply a sum of the viscous losses and kinetic energy losses. Okay, so this equation 3 is called as the Ergon's equation. This is applicable for all range of all range of fluid flows, whether it is the laminar or turbulent or transition, whether Reynolds number is from 0.01 to it's up to infinite. This equation is applicable for all range of fluid flow rates. Okay, so I have already given the what is minimum fluidization. The same relation what is called definition will be given here. Okay, the explanation will be simply given in the form of written terms. So we have to see what is the pressure drop at the minimum fluidization. So at this minimum fluidization condition, pressure drop counterbalances the force of gravity or weight of the bed by allowing buoyant force of the displaced fluid, right? Okay, what happens in this diagram? The fluid applies upward thrust, that is buoyant force on the solid particles, and the weight of the bed will be acting in the downward direction. Okay, if you increase the velocity, the pressure drop also increases. So this weight of the bed will be counterbalanced by this upward thrust and pressure drop. Then only the particles will start moving, right? Okay, so that is given by this expression here. So pressure force plus buoyant force okay, this pressure and buoyancy force per unit area is counterbalanced by the weight of the bed, right? Okay, so from this delta P equal to gravity force or bed weight minus buoyant force. So mg of the bed per unit cross section minus rho f Vf, since this is the fluid upward of the fluid thrust, right? So that is rho v Vf into g divided by S naught. So m is the mass of the solids, that is density of the solids and volume of the solids. S naught L, this 1 minus epsilon is nothing but the, since the solids are packed in between, the gaps will be there, right? So that is given by the porosity. Okay, how much voidage, how much voids are there all over the bed. If I say that is a fraction of the voids. So if your total volume is 1 means 1 minus epsilon is the, this is the void fraction, 1 minus epsilon is the solid fraction, right? This is S naught cross section area of the total bed, and L is the length height of the bed. This is the total volume into volume fraction of the solids will give the total volume of the solids by excluding the voidages. Okay, here also, since in case of buoyancy force, the volume of the fluid will be measured, amount of the volume of the displaced fluid will be measured in terms of the volume of the solids, right? Okay, since we cannot measure the how much fluid volume is displaced, so this is measured in terms of the volume of the solids, that is nothing but Vf equal to volume of the solids. So density of the fluid, so volume of the solids into G per unit cross section. So here the cross section will be get cancelled. So delta P equal to rho P L 1 minus epsilon into G minus rho F L 1 minus epsilon G. By taking L 1 minus epsilon G common, you will get delta P equal to G 1 minus epsilon into rho P minus rho F into L. This much amount of pressure, minimum pressure, okay, is required for fluidization. Okay, at this condition the epsilon is called as EM, minimum porosity. Clear? So this equation again we can represent as delta P equal to G 1 minus epsilon M rho P minus rho F into L. Thank you. So in the problem they have given the density of the sea water and density of the resin beads, diameter of the tower they have given, diameter of the particle they have given, diameter of the particle is given, epsilon is given and G is given. They have asked us to calculate what is the pressure drop required for minimum fluidization. So from the concept I have explained, the minimum pressure drop required for fluidization is delta P equal to 1 minus epsilon M rho P minus rho into G into L, right? So they have asked us to calculate pressure drop required. Length of the bed height not given, so we can calculate pressure drop per unit length. So by substituting the corresponding values, epsilon equal to 0.1 minus epsilon equal to 0.6 and rho P minus rho, the difference will be this much, and G is 9.81. Substituting we will get 1795 Pascal per meter pressure drop per unit length. Clear? I hope you have understand the problem. If you have any doubts, please mention in the comment section. If you like the video, please subscribe and share. Thank you.